So this is my last topic for today. So the final thing that I want to show you is what we call model fit metrics. So this is some way of describing the proportion of the variation explained in the data by your model. So when you talk about regression model fit metrics, there are quite a number, and I'm just going to pick one, which I think is there are many of them, all of them have strengths and weaknesses. I'm just going to pick one that we can use because I think it's the one that has the most natural interpretation and it's useful. It doesn't mean that it's necessarily that much better than any of the others, but the others all have their flaws. And you can see that the one that I've picked is the one that's in blue, or hopefully you can see that's in blue, which is called R squared. Okay, so there's another metric called adjusted R squared, but the one that I'm going to choose across AIC, adjusted AIC, or corrected AIC, or BIC, blah, 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 blah. We pick one of the possible many model metrics. The one that I've picked is R squared. It also has this, for me, it's easier to explain because it's very similar to the way that you've seen things before in proportioning up the variation. So the way that you calculate the R squared value is that you find the total variation in the data around the grand mean. Sounds pretty similar. You find the variation that can be explained by the model, and then you find the variation that's unexplained by the model, and you compare them. So very much similar to what you've seen before. So if we see this though, the way that I've visualized this is, so we've got our data. Remember I said that the trend line that we fit will always pass through the sample mean, so I've just identified that anyway. And when I've got my trend line, you can see that for a given x value, which I've denoted xi, so this is just one particular x value, I've got the grand mean of the data, I've got my trend line, and I've got my actual observation highlighted up there in red. So I look at where my trend line is going and I say the difference between the mean of the data, so where the y is, so the grand mean of y, and where my trend line goes is the explained variation. So that is the variation, or that vertical distance is the variation that the model can explain. The bit above that, so the bit between my fitted value, my y hat, and my actual observation is the unexplained variation, or my residual variation. So I'm saying that a portion of the variation, the difference between the mean of the y and where my predicted value is for a given x, is my explained variation, and the bit that is not explained is the residual or unexplained variation. And we do that for each data point that we have. So then we add all of those distances up, or more specifically, we add up those squared distances because positives and negatives, as we've seen before, would cancel out. So the way that we have this, and I don't know why I'm not moving forward, is we say the total variation in the data, so the total variation, that is the explained variation and the unexplained variation. So you can see for a given point, I've broken up the total distance between the mean and the actual data point into explained and unexplained variation. So the total variation in the data is equal to the explained variation plus the unexplained variation. Now then, if you divide both sides of that equation by total variation, as I've done there, you can see that total variation divided by total variation is going to give you 1. And then on the right-hand side, you've apportioned that 1 into the proportion of variation that can be explained and the proportion of variation that is left unexplained. So our R squared metric is equal to the explained variation divided by total variation. So that is how much of the variation in the data the model explains. And it's a value that's bounded between 0 and 1. And you can see here in R, the R squared is actually reported as multiple R squared. There are many, there are other metrics. This is just the way that R has chosen to report it. So the value multiple R squared is the coefficient of determination. What do you denote it as? You denote it as R squared. What is R squared? R squared is the explained variation divided by the total variation. So it's the proportion of variation in the data explained by the model. right? Very, very common reporting metric. Where does it sit in R? It sits somewhere here, multiple R squared. So here's a different model that I've estimated, and you can see another multiple R squared. So how would I interpret that value of that 0.9155? I could say that 91.55% of the variation in the data is explained by my model, okay? So multiple R squared, we just report it as R squared, and what do you say? You say it's the proportion of the variation in the data explained by the model. So this example is based on someone that I teach with in the level, an honours course basically, and this is some code that Michael had originally written that I've adapted for our purposes here. So we've got some hermit crabs, and actually I was thinking about this. I'm really not sure whether I should have weight on the vertical and time active on the horizontal, or time active on weight. Does weight explain time active, or does time active explain weight? I actually don't know. Like after I did this, I thought about it a bit. Here I'm going to say that weight can explain time active. Okay, I might have actually got this around the wrong way, but I'm going to stick with that. Weight explains time active. So there's my data. It's looking downward sloping. It's not a perfect linear relationship, but it looks on the linear scale, it looks pretty okay. So I'm going to fit a line to that. All right, so there's the line that I fit. And when I go into R, you can see that the intercept is 17 and the slope is minus 0.23. Okay, so that's just telling me the minus, I've got a downward sloping line. So what I want to do next is I want to compare this to what's often called the null model, or the null model would be a line at the mean. So I'm looking at my null model. My null model would be a model at the sample mean. So by null, I mean that I have no explanatory variable. All right, so I would have slope of my line is what I've fitted, okay, and I've got an intercept of 17.2 and a downward sloping line of 0.23, so negative slope. If I just found the mean of the data, I would have got a value of 4.4, and I'm going to call that my null model. All right, so I'm going to plot that on here now. So you can see there I have it. I'm showing my trend line and my line where I've just fitted the grand mean to the data. Now, what I'm putting on here, so you can just see these points that are appearing. For each xi value, I'm showing it at the grand mean. So while we've got these lines, you can see I don't have data points everywhere. So I'm just adding wherever I have an X observation, so a measurement, I'm showing that also on the grand mean line. Now what I want to do is show you the total variation in the data. So the total variation in the data is the distance between the mean and the actual data observation. So you can see here these vertical distance. So I'm going from, for each X point, the vertical distance. Some of them are positive, some of them are negative. How do I calculate the total variation? I calculate the sum of the square distances. Okay, so that's my total sum of squares. The next thing that I'm doing is I'm adding where my predicted values are. So see these red dots? These are my predicted values. And for these guys, what I'm doing is now I'm going to show the red lines. So the red lines are the distances that are left unexplained. So it's my error sums of squares. This is the variation that's not explained. If I now put on my green lines are the difference between the mean and my data point, and the difference between the mean and my data point is equal to my explained variation. So if I give all this a key, you can see that I've got a whole bunch of things going on here. What have I got? I've got the total variation in the data is the black lines, and my explained variation is the green lines, unexplained variation, the red lines. The explained variation is the sum of those green lines squared, or the sum of the squared green lines. The total variation is the sum of the squared black lines. And when I work that all out for this model that I've fitted, the multiple R squared reported by R, or just the R squared, is 0.83, which means that 83.3% of the variation in the data is explained by the model. And that is an opportune time to go through or to end. Next week, we're going to look at a whole bunch of examples.